Hello everyone, this is lecture 6 of course PE 500. In this lecture, we will switch the gears to deal with numerical methods for solving ordinary differential equations. And we are going to use the numerical methods because not all differential equations can be solved analytically, such as including complex forcing functions on the right-hand side. For example, some biological systems may involve nonlinearities functions such as sine of y and the exponential of negative y. Also, they can include time-varying and dependent parameters or complex forcing functions. So the idea here, if you are facing a complex problem or a complex differential equation from the type ordinary differential equation, then you can switch the gears from dealing with analytical solutions to deal with numerical solutions. We are going to discuss in this lecture Euler method and improved Euler method and Runge-Kutta RK4 method. And for each we will discuss different details once you get an example or a question until you retrieve the final answer. So let's begin with the Euler method. So what is Euler method? Euler method is a first order numerical procedure that solves ordinary differential equations with a given initial value. Euler method approximates the solution to an initial value problem, IVP, which is governed by a first order differential equation by simply taking small steps along the tangent line at each point. This method provides a simple yet effective way to estimate the behavior of dynamic systems when analytical solutions are difficult or impossible to obtain. This method is particularly useful when an analytical solution is difficult or impossible to find, as we mentioned from a while, and you are modeling a real-world biological system such as drug elimination from the bloodstream, population growth, and enzyme kinetics. So simply, you have an ordinary differential equation, dy by dt equals a function between t and y. And you have an initial condition. Y of t is the unknown function that we want to approximate. T is the independent variable, which is of in time. F of t and y is a known function that describes the rate of change of y with respect to t, and y naught is the initial value at time naught. The goal here is to numerically estimate y of t at discrete time points from t0, t1, t2 until you reach to tn minus 1, which is the last point, with a fixed step size h. So how simply we can do that? We can use directly this equation. But how this method or equation is derived? Simply, Euler method is based on the Taylor series expansion of the unknown function y of t around a point tn. So if you apply the Taylor series expansion here, y of tn plus h, it will get ytn plus h multiplied by the first derivative of tn plus h squared over 2 multiplied by a second derivative of y of tn, and so on. So in Euler method, they said we can approximate that expansion to make it an approximate solution by simply taking the first two terms, which are ytn and h multiplied by the first derivative of tn. And from a while, we mentioned that the first derivative equals to a function of the tn and yn. So simply we can substitute here by that value. So the next value of y will equal to the first value plus h multiplied by a function of tn and yn. And this function is the core of the Euler method. Yn here is the approximate solution at time tn. As mentioned, h is the step size. And also as mentioned, f of tn and yn is the derivative evaluated at step n. So if we have an initial value here and we have a known step size, we can simply substitute in this equation to get the next value. By doing so, we can then get different values at different time steps, t0, t1, t2, and so on. And these values will be our solution at the end of the required time. So how to use the Euler method to get the final solution? And then we can compare that solution with the exact solution if it exists. Simply, we have a differential equation, and we have an initial condition, and we are given a step size and a time interval from a beginning and ending time slots, T naught and Tf, T final. So we will initialize our environment by simply setting T naught and Y naught, and these are the initial values or the initial conditions, and define the step size which is given in our question, and compute the number of steps that equal to the final time minus the initial time over h. So if we have from 0 to 5 with a step 1, then it will be 5 minus 1 over 1. It will be n equals to 5. So with that, we will need to compute the Euler formula 5 times. After that, in the next step, we will iterate using the Euler formula, which is here, for each step from n equals 0 until we reach n minus 1. And we start by 0 here because it will be the initial value or the initial condition. After that, we will keep track of all Tn and Yn values, as these values can be plotted and analyzed further. And also we can use these values to compare with the exact solution. So if the exact solution exists, we can compare it with the numerical approximation to assess accuracy. Simply, we can plot each of them, calculate the error between the different points, and we can say that the Euler method in that example has an error of a certain value. So in the three methods, we are going to introduce two terms. One is called local truncation error, and in short LTE, and the other is called global truncation error, and in short GTE. So simply, what is the difference between both of them? The LTE is the error introduced at each time step or step size, and the GTE is a cumulative error over the entire interval. And for each algorithm, there are specific values for LTE and GTE. So for the Euler method, we have a LTE, which is proportional to h squared, and h here is a step size, and the global truncation error or GTE is proportional to h. And by introducing the different methods, by the end, we can use a method with a high accuracy, but it will come to the cost of the computational cost. So if you need an accurate approach, but there is no matter about the computational cost, then simply you can use an effective method. And if you need a faster one, but less accurate, then you can use another method. So for now, let's remember these two values, which refers to the complexity or the error complexity, until we introduce the different methods. And by the end, we will compare between all of them so that we can mention which is the most accurate and which is the most method that consumes resources. And as a tip for the Euler method, you can simply reduce the step size to improve the accuracy, but this will come to increase the computational cost. Also, to observe how reducing the step size improves the approximation and the accuracy, simply you can try repeating any example in hand with different step sizes, for example h.5 and h.1, and compare between both of them, and you will observe in most examples that reducing the step size will increase the accuracy and the approximation. So let's start by this example. We have a model for the drug concentration in the bloodstream, which is governed by this equation, dc by dt equals to negative k multiplied by c. And we introduced that equation and that model earlier in the previous lectures. C of t here refers to the drug concentration at time t, k is the elimination rate constant, and c naught is the initial concentration. And we have an initial condition here, c of 0 equals to c naught. 0 here is the time, and we will assume these values for c naught, k, h, and the interval. C naught equals to 100, k equals to 0.2, and we have a step size of 1 hour and interval of t between 0 and 5. So 0 here will be the initial time, 5 will be the final time. So simply, if we need to compute the number of steps that we need to calculate as an approximation, then it will be equals n equals to the final 5 minus the beginning 0 over the h, which is the step size 1. This will be 5. So we need to compute 5 iterations of the Euler method. So let's substitute a by the value 0.2. So we'll get dc by dt equals to negative 0.2 multiplied by c. And we have these initial conditions and values. This is our Euler method, so we need to iterate over 5 steps using this formula. So let's substitute first in this equation by our values. H here equals 1, and the first derivative equals to negative 0.2 multiplied by c. So simply, the next step, or c of n plus 1, will equal to cn minus 0.2 multiplied by cn, as h equals 1. We have here cn and cn, so simply this will get 0.8 multiplied by cn. So the final equation, get the next value, will equal to 0.8 multiplied by cn. So from that, we can observe that the next step is a decay from the earlier step by 20%. We have at n equals 0 that c naught equals 100, and this is given by the initial condition. Substitute in the Euler formula multiple steps, you will get at n equals 1 by substituting 0.8 multiplied by 100 equals to 80. Again, 80 multiplied by 0.8 will get 64, and by doing so along the 5 iterations, you will end with that value, which equals to 32.768. Now, we have these values. We can compare with the exact solution if we have it. So if you remember, this was the exact solution, and you can derive it using handwritten calculations, but you will end by that equation. So simply, these are our approximations, and by substituting with the different e values, we will get these exact values. And the absolute error here in this case will equal to the absolute difference between the Euler and the exact value. So simply, 100 minus 100 is 0. 80 minus 81.873 equals to that value. And doing so, you will get these absolute error values. And as seen here in this example, the Euler method gives a reasonable approximation. But if you notice here, the error accumulate over time, especially when you are using larger step sizes. And here we are using h equals 1. If you repeated this example by h equals 0.5 or 0.1, then the error will be reduced. But the number of steps or iterations will increase. So we are going to increase the computational cost, but instead we will reduce the absolute error. So simply, in any example, handle your formula, which is the Euler formula, by getting the first derivative and substituting and simplifying the equation, and then iterate over number of steps equals n, and then you can compare between the exact solution and the approximate one and get the final error or the cumulative error. Now we need to apply that using Python and MATLAB. So let's go to script lecture 06, lab exercise 1, Euler for MATLAB and Python. Here we import the necessary libraries, NumPy for numerical operations, matplotlib for plotting, and we imported pretty table for plotting tables on the command window in a pretty way. Here we define the Euler method that can be adaptive to different examples, and you can simply change the constants. Instead of using c naught, you can use the constant in hand, but the content here will be similar. Here we got different values, c naught, k, which refers to the concentration and the drug elimination constant. H is the step size, t span is the time span from the time start to the time end, and this function should return two lists or two NumPy arrays, one for the time vector and one for the approximation or the concentration values. At the beginning, we initialized the approximation to be a 0 vector with the same length of the t Euler, and here we are making a range to refer to the time steps. Simply, we are making a range from the time start to time end with a step size h. We added the initial value here to be c naught, which is our initial condition. After that, the next value in each iteration will be the current value plus h multiplied by negative k multiplied by the current value. If you remember, the equation was like that. The current value plus h multiplied by the first derivative. And the first derivative is that. negative k multiplied by the current value, which is c. So we simply applied that here. We encapsulated again all of that in this equation, and then we defined the parameters as in our example. Then we called the Euler method and got the Euler and C Euler, the time and approximations. Then we defined the exact solution so we can compare it. And to do so, we used the absolute error between C Euler, which is our approximations, and we used a linear interpretation from the T exact and the C exact with the same time with the Euler method, simply because in the Euler method we used 5 points or 6 points, which refers to the n value that we calculated, but in the exact solution we made another range from the beginning until we reach the end with 100 points. So if we compared using the indices, this will be wrong, because the first index here will be different than the first index here. So simply we can make interpretation by giving the required time and what do we need to interpret, which are the exact solution here and here. So this will get values for the corresponding times in the T Euler. Now we have two vectors. We can subtract both of them together and get the absolute value. This will be the absolute error, and this will be another vector. We printed the parameters and created an object from the pretty table. The pretty table accepts an argument called field names, which refers to the header of the table that we are going to print. And here we are going to print the time, Euler method, exact solution, and absolute error. And then we looped all over the values and added row in the table. By adding these rows, we can, by the end, print this table. What are we printing here? The time, rounded to 3 decimal points. The approximated solution, which comes from the C Euler, the approximations that we calculated here from the Euler method, and the absolute error, which is here, which was calculated here. And the exact solution, we used the same approach for the interpretation, but at a specific time point t, using also T exact and C exact. We have here a value, we can print it rounded to 3 decimal points. This will print a table, and this will plot the results. The exact in red and the Euler in blue. We added labels, title, legend, grid, and we adjusted the layout to prevent the overlapping, saved the figure, and displayed it by the end. And this will be the output. These are the printed parameters, and this is the table, which is out of the pretty table. This is the header, as we mentioned, and these are the different rows: time, Euler method approximation, exact solution, and the absolute error. And you can compare these values with our calculated values. And also this will be our plot. In red, it's the exact solution, which is here, and in blue, it's Euler approximation, which is here. As you notice, at the beginning, there is no error, and the error increases by increasing the steps. The error here increases to be like that, and if you are going also to increase the interval, this gap will increase. As we mentioned, the global truncation error will increase by increasing the steps, and this was for h equals 1. But as we mentioned, if we reduced the value of the time step or the step size, for example h equals to 0.5, this will increase the complexity or increase the cost, which refers to the number of iterations. Here we have more iterations, but on the other hand, the cumulative error will decrease. Here at the end was 4 or around 4, and here it reached 1.9. If you try this example again one more time, but instead of 0.5 to 0.1, you will find the absolute error is decreasing, and these two plots or curves will come closer together. And for MATLAB, we did the same. We initialize the simulation parameters called the method, and we mentioned in MATLAB, if you need to write a script and define a function, write this function at the end of the code, as we did here. That function did the same as we illustrated in Python. Then we generated the exact solution and made interpretation to get the absolute error, printed the simulation parameters, and displayed the results as a table. Then we created the figure, and don't forget hold on and hold off, added labels and title, added the legend and the grid, and saved the figure and displayed it. Once you execute the code, you will find the printed parameters and this table. Also, you will find this figure. You can also compare between the Python results and MATLAB results. You will find both of them are similar. Now, let's introduce a second method. It's called improved Euler method, and it has another name, Heun's method. And this method is an improved version of the discussed earlier method, and it's a predictor-corrector algorithm that enhances accuracy of the basic Euler method by using an average of two slope estimates, the slope at the current point and the predicted slope at the next point. And using this approach will lead to a more accurate approximation of the true solution, especially for systems where high precision is important, such as drug concentration dynamics or population growth modeling. Again, we have dy by dt equals to a function that describes the rate of change of y with respect to t, and our goal again is to numerically estimate the function y of t at different discrete time points t naught until we reach tn minus 1 with a fixed step size h. In the improved Euler method, we will use two steps per iteration. One is called the predictor step, and the second is called corrector step. The predictor step is to estimate the next value using the earlier method, which is traditional, as we mentioned in the Euler method, the current value plus h multiplied by f of tn and yn, and this will get y of n plus 1, but here we added a star, because this will not be the final value. This will be only the prediction. Now we need to make the correction, simply by taking the average of the two slopes between f of tn and yn and the predicted one of the next step, which is f of tn plus h and yn plus 1 star. Getting the average of both and substituting in the same equation, we will get yn plus 1. So the correction here simply is doing the same with Euler method, but again repeating the same with an average of the first slope and the second slope. As we noted here, the slope at the current point and the slope of the next point or the predicted slope. The improved Euler method improves the basic Euler method by simply reducing the error through slope averaging, and this will present better approximations between the different points. For the LTE or the local truncation error, the error introduced at each step is proportional to h cubic, while the GTE or global truncation error is proportional to h square. To compare between both methods, it's obvious that we can say that this method reduces the error significantly without requiring small step sizes. By that, we will improve the accuracy, as we implemented a corrector step between the current and the predicted points. And we also will notice that when we deal with the same example, but using the improved version of Euler method. So using the same example with the same configurations and time interval, we will do these steps. Let's define our equation again. dc by dt equals to negative 0.2 multiplied by c. And let's define our initial values and the configurations. Let's follow these two steps in each interval point. The next step star equals to the current step plus h multiplied by f of tn and cn. Substitute. This will be that value. Here h will be 1, so it will result to cn minus 0.2 multiplied by cn. That will result to 0.8 multiplied by cn. And this should be similar to the basic Euler method. But instead again of using the next step as a final value, we are adding a star here so that we can correct it later. Next, we will substitute in the corrector step. The final predicted value will be the current value plus h over 2 multiplied by f of tn cn and f of tn plus h and cn plus 1 star. This again will be that. So substitute here. And this will be defined by simply substituting by every cn point to be cn plus 1 star, like here. And also if you have a term of t, we can substitute with the term instead of t. So the final equation for Cn plus 1 will be like that. Cn plus 1 over 2 or half, because h equals 1, multiplied by negative 0.2 Cn minus negative 0.2 Cn plus 1 star. To make it easy for our solution, we made this table. At n equals 0, we got C naught equals to 100. Substitute to get that, 0.8 multiplied by 100, so we have C1 star equals to 80. Substitute in the corrector step, we will get that the final C1 value equals to 100, which is Cn, plus 1 over 2, which is 0.5, multiplied by negative 0.2 multiplied by Cn, which is negative 0.2 multiplied by 100, minus 0.2 multiplied by 80, which is this value. Simplify that and calculate the final result. This will be 82. So instead of 80, it will be 82. Do the same. Now we have C1 equals to 82 multiplied by 0.8 to get C2 star, which is 65.6. Substitute in the corrector step to get a final value of C2 to equal to 67.24 instead of 65.6. Doing the same all over the steps, we will get a final C5 by around 37.07 instead of 36.17. If you made a comparison with the exact solution between the improved Euler and the exact solution, the values we calculated here, you will reach that absolute error. If you remember, in the Euler method, we reached an error of 4, but here we reached an accumulated error of 0.286. So it's obvious now that the Euler method gives significantly smaller errors compared to the standard Euler method. We need again to write a code for the improved Euler method, and also we can calculate and plot all of the methods together to compare between them. So go to lecture 6, lab exercise 2 improved. We imported the same libraries, added the same Euler method that we illustrated from a bit, and added a new method called improved Euler method that takes the same parameters and do the same, but instead of only getting the predicted value, here we are getting two slopes. One using this equation, minus k multiplied by the current value, and multiplying by h to get the predicted value. This was Euler. Here we added the second slope, which is also the predicted value multiplied by k. Now we have slope 2. We can add both of them together, multiply by h over 2, adding it to the current value to get the next value. This function will return the time and approximation for the improved method. Now we have two methods. We can call both of them, define the exact solution, get the absolute error, but this time between the exact solution and improved Euler method, print the parameters and print the table. And here we added the normal or the basic Euler and the improved one in our table. So you will find a change in the header here. We added Euler and improved Euler. Also we made a plot to plot the exact in red, the Euler in blue, and the improved Euler in green. We added the same labels, title, grid, legend, and adjusted the layout, saved the figure, and displayed it. After executing the code, you will find the following parameters and the following table. Compare between the calculated value, 0.286, approximated to 3 decimal points, which is here. Also, this was our basic Euler method curve. But if you notice, these two curves, which are the exact solution and the improved Euler method, you will find that both of them are close enough together. If you go to MATLAB, you will find the same steps. Define the simulation parameters, executed the Euler method and the improved Euler method, generated the exact solution, and made a comparison to get the absolute error between the improved Euler and the exact solution, printed the parameters and the table, created the figure, exact in red, Euler in blue, and improved in green, created and defined the configurations for the plot. Here are the defined function for the Euler method, and here for the improved Euler method. If you executed the MATLAB code, you will find similar results. This for the parameters, this is the table, this is the final accumulated error between the improved and the exact. this is the curves, Euler, and for the improved and exact, they are close enough together. Now, let's move to the third approach, which is called Runge-Kutta Method. And Runge-Kutta methods are a family of numerical techniques used to solve initial value problems governed by the first order ordinary differential equations, and it's on this form dy by dt equals to f of t and y. And in Runge-Kutta methods, we are estimating y of t at discrete time steps using multiple intermediate slope estimates. And this will provide better accuracy than simpler methods like Euler and improved Euler methods. One of the most common variants of Runge-Kutta is called Fourth-Order Runge-Kutta Method, RK4, which we are going to use here. So RK4 method uses 4 evaluations of the derivative per step to compute a weighted average slope that will give a high accurate approximation. So instead of nothing in Euler method or one average in the improved Euler, here we are using a fourth order, which means 4 evaluations per one step. For sure, this will increase the computational cost, but instead it will decrease the error and improve the accuracy. For each step in RK4, we will calculate K1, which is the basic, h multiplied by the first derivative. K2 is similar, but here we are adding h over 2 to tn and k1 over 2 to yn. And for K3, we are doing the same, but instead of K1, we are using K2. And here is the last, K4 equals to Tn plus h and Yn plus K3. So it's obvious here that each intermediate K value is propagated to the next one. For the intermediate 2 steps, we are dividing by 2. And this is the RK4 algorithm. By calculating K1 to K4, which are 4 intermediate steps, substitute here the current value plus 1 over 6 multiplied by K1 plus 2 K2 plus 2 K3 plus K4. And 6 here because we have 2 plus 2 plus 1 plus 1 equals to 6 to be a weighted average. Regarding the accuracy for the local truncation error for the RK4 method, here each step is proportional to h to the power of 5. And for the global truncation error, the cumulative error over the entire interval is proportional to h to the power of 4. For sure, this will make RK4 a fourth order accurate method, meaning that halving the step size reduces the entire error by a factor of 16, and this method is excellent for real-world simulations where precision matters, and we can say that RK4 is the most accurate among these 3 methods, but it consumes time, and on the other hand, the Euler method is the least accurate, but it's fast. Using the same method for the drug concentration in the bloodstream, this is our equation, and these are the same given parameters and values. Let's calculate one iteration manually from T0 to T1 to understand how we substitute. These are our initial values. Simply, let's add the different formulas from K1 to K4, then substitute h multiplied by the first derivative of T0 and C0. H is 1, T0 is 0, C0 is 100. Substitute by this value here, you will get 1 multiplied by negative 0.2 multiplied by 100 equals to negative 20. Do the same for the next one. T0 plus h over 2 equals to 0.5. C0 plus K1 over 2. C0 100. K1 over 2 is negative 20 over 2 is 100. So this will be negative 90. Substitute by 0.5 and negative 90 here. This will get negative 0.2 multiplied by 90 equals to negative 18. Do the same for K3. T0 plus h over 2, which equals to 0.5. C0 plus K2 over 2. C0 is 100. K2 over 2. Negative 18 over 2 is negative 9. 100 minus 9 will get 91 multiplied by negative 0.2 will get negative 18.2. For K4, T0 plus h is 0 plus 1 is 1. C0 plus K3 equals to 100 plus K3. K3 is negative 18.2, which is here. 100 minus 18.2 will get 81.8 multiplied by negative 0.2 would result in negative 16.36. Now we have the values from K1 to K4. Substitute in the update equation or the final equation. K1 plus 2K2 plus 2K3 plus K4 will be these values. Divide by 6 and add to the initial value, which is 100, will result in 81.873. If you compared that value with the exact value, which is here, we will find that the least error is found by the RK4, which is around 0 if it's rounded to 3 decimal points. To do that, using Python and MATLAB, let's go to exercise 3, RK4. We defined Euler, improved Euler, and RK4, so we can compare between the three methods. In the RK4, we got the same parameters, and here we got K1, K2, K3, K4, and substituted in the update equation to get the next value. By doing that on all the steps, we will get a final time and approximate solutions. Defining the same parameters, calling the Euler, improved Euler, and Runge-Kutta 4. Then we defined the exact solution, got the absolute error between the RK4 method and the exact solution. Then we printed the parameters and the table, and inside this table we printed all of the methods. Then we plotted the results and displayed it by the end. When we execute the code, you will get these parameters and this table. As you notice, this is the least error among the three methods. And if you compare between the exact and RK4, they are very close together. Also, on the curves, you may not notice the RK4 method and the exact because both of them are close enough, so you'll find that one is above the other. For MATLAB, we did the same. Defined the parameters, got the output of the three methods, generated the exact solution and calculated the absolute error, then printed the simulation parameters and displayed the table, created the figure, exact, Euler, improved Euler, and RK4, defined the configuration, saved the figure, and here we defined a new method. It's called RK4 method, which is performing the same K1, K2, K3, K4, and the update summation h over 6 add to the initial value to get the next predicted value. If you executed the code, this will be the parameters, the time or the table, RK4 exact methods, the absolute error, and this is the corresponding plot. So in this lecture, we introduced some numerical methods to solve the ordinary differential equation. We began with the Euler method, then the improved Euler, and ended with the RK4 method. We introduced two terms, the local truncation error and the global truncation error, and we found that by the end, the RK4 method is the most accurate, but it consumes more resources compared to the Euler method. So if you are ordering them from the most accurate to the least accurate, we can say RK4, then improved Euler, then Euler at the end. And if you are comparing between the three methods regarding the computational cost from the fastest to the slowest, we can say that Euler is faster than improved Euler, and both are faster than the Runge-Kutta 4. So it's a trade-off. If you need something fast, but you don't matter with the accuracy or the error, then you can use Euler. If you matter with the accuracy over the time and cost, you can use the RK4.